Now let's start with quantization. Quantization. As the name suggests, quantization, like if there is a quantity and we take it into parts, it's basically quantization. So for quantization, k equal to 2 raised to power n. Sorry, n raised to power of 2. Yeah. So what is k here? K is increments. So if there are analog signal, quantization is basically dividing that signal into quantas, into segments. So like if this is 0, this is plus k, this is plus k, that is then it becomes 2k, 1k, like that. So k increments. How many k increments? K equal to n raised to power of 2. So n is here bits. It depends on how many bit ADC we have taken. So if it is 3 raised to power 2, so this is 3 bit ADC. Okay, and then we get Q equal to, there is one more formula, V max minus V min by again. So here Q is resolution and V max and minus V min. So I'm really confused if it's 2 raised to power of n or if it is n raised to power of 2. Tell me in the comments. So Q is the resolution of V max minus. So let's understand with an example. So let's say we have V max equal to 10 volt and V min equal to 0 and it is 3 bit ADC. So we get Q equal to 10 minus 0 by this. So it will be 1.25, right? That's 1.25 volt. This means that our resolution is 1.25 volt, which obviously means that we will divide it into 0 to 1.25, then 1.25 to again plus the 2.50, then 2.5 to 3.75, and like this we get 10 minus 1.25 is, I think so, 8.75. Yeah, 8.75 volt. So how many states are there? So it is 2 and power is 3, so it gives us 8. So there should be 8 increments, right? Here we can see there should be 8 increments. So there should be 8 states. Let's count. 0, 1, 2, and it should be 8. It should be 7 actually. So 8 states. We take this state as 0. And then the next part to quantization was encoding. So in encoding, we name the states like 000. It's because it's 3 bit. 001 and 010, that's equivalent of 2 in binary, and 27 is 111. You can check. So likewise for 4-bit likewise for 4-bit ADC we get 4 bits, like maybe 1 1 1, like that. So let's see if there is an analog signal and we convert it and we use a 3-bit ADC, and we saw in the previous example that K was 1.25 volt. So here we will increment it by 1.25. So let's see, maybe this, because it's a continuous signal. And then we when it was 3 no, let's take a simpler example because it will be quite a work. So if we take 2-bit ADC, so and it's again 0 to 10 volt, so Q will be 10 by 2 raised by 2, so 10 by 4, and this will be 2.5 volt. So this will be 0 to 2.5 volt, then 2.5 to 5 volt, then 5 to 7.5 volt, and then 7.5 to 10 volt, right? And this will be state 0 1 2 3, and again 0 0 1 1 0 1 1. Yes. So if we have to divide this state would be taken as 0 0. Let's take this at 0 1 and this as 1 0, and this should be 1 1. So how would be making digital signals? So this shall be 0, and then this is, let's say this is 2.5 volt. We have to make 4 states, so then again 2.5 volt, and then again 2.5 volt, and then again 2.5. Let's see. Okay, now this is 0, and then this is 0 1, so this and this, okay, and then it touches here, so then it touches here, so and then here, so this would be the digital signal here. Now if we get 3-bit ADC, obviously 2.5 volt resolution will get converted to 1.25 volt, which would mean that like states would be 0 0 0 0 1 0 1 0 1 1 1, and then like till 0 1 1 and like 1 1 1. So obviously here also states would be much more, like 0 1 and 1 0 and like that, and then the signal would be like much more precise. So which shows that because resolution is low, right? So this shows that more bit, more information. So there is a ADC called MCS 12. It has maximum of 10 bits, so more information, better representation with more information, right? So the lesser is the resolution, more is the better representation of the signal. Also we see that k is k decides are discrete states. Quantization is dividing the segment, separating the input signal into discrete states. And what's the encoding? Encoding is assigning unique code, digital code, to each state for input into microprocessor.